Tonight we're going to explore a hole in our map of the universe. Not a black hole out in the dark, though there will be many of those before we are done. A hole in the catalogue, a missing size. For more than 50 years, astronomers have found black holes as small as a few dozen suns. They have found black holes as large as tens of billions of suns, and almost nothing in the vast stretch between them. That gap spans nearly 3 orders of magnitude. Think of it as a staircase. The bottom steps are solid stone. The top steps are solid stone. The entire middle section has never once been shown to exist. That should stop you cold when you sit with it. We can weigh a black hole the size of a city. We can weigh one that could swallow our whole solar system without slowing down. But the ones in between, the ones that must connect the two, have hidden from us for half a century. There is supposed to be a whole class of them out there, a missing rung. And every time someone thinks they have finally caught one, it slips loose again. Tonight we're going to follow that hunt. We're going to walk from the smallest black holes we know, out across the empty middle, all the way up to the monsters. We're going to meet the handful of strange objects that might, just might, live in the gap. Some of them sit closer to Earth than the Milky Way's own central black hole. One of them announced itself as a ripple in the shape of space that lasted less than a second. One of them was only found because it slowly tore a star into glowing threads. If these quiet cosmic mysteries are worth chasing with us, leaving a like or subscribing keeps the channel searching. Every episode lives on Spotify too, for nights with the lights already off. That is the only time I will ask. Now let's begin. Start with what we are sure of. A black hole is not a thing so much as a place where gravity is won completely. Enough mass has been packed into a small enough space that nothing can climb back out, not even light. The boundary around it, the point of no return, is called the event horizon. Cross it, and every path forward leads deeper in. There is no visible surface. There is nothing to land on. There is only a region of space from which no information ever returns. The smallest black holes we know form when a massive star dies. A star is a balancing act that lasts millions of years. Its own gravity is forever trying to crush it inward. The nuclear fire in its core is forever pushing back out. For as long as there is fuel to burn, the star holds its shape. But fuel runs out. When a star far heavier than our Sun exhausts the last of its core, the outward push fails in an instant. Gravity has been waiting patiently the entire time. Now it finishes the job. The core collapses. If the collapsing core is heavy enough, nothing can stop it. It falls all the way down into a black hole. These are the stellar mass black holes. The confirmed ones weigh roughly 5 to 70 times the mass of our Sun. That is the whole known range for a black hole born from a single dying star. 5 suns at the light end, around 70 at the heavy end, and most of them clustered somewhere in the middle. A black hole of 10 solar masses is a genuinely tiny object. Freeze it in place and measure it. Its event horizon would be less than 40 miles across. A black hole the mass of 10 suns folded into a sphere you could drive across in under an hour. It helps to walk through that birth slowly, one stage at a time. Take a star far heavier than our Sun, perhaps 20 or 30 times its mass. For millions of years it fuses hydrogen into helium in its core. The heat of that fusion holds the star up against its own crushing weight. When the hydrogen runs low, the core contracts and heats, and the star begins fusing helium into carbon, then carbon into heavier things, neon, oxygen, silicon. Each stage burns faster than the last. The hydrogen phase can last 10 million years. The final silicon-burning phase can last a single day. The star is racing toward a wall it cannot see. At the very end, the core is fusing silicon into iron, and iron is the wall. Iron fusion takes energy in rather than giving energy out. So the fire that held the star up simply switches off. In less than a second, the core collapses. The outer layers rebound and blast away in a supernova bright enough to be seen across a galaxy. And what is left at the centre, if the core is heavy enough, is a black hole. You have just watched a star spend 10 million years building itself. Then it falls inward in the space of a heartbeat. It leaves behind a dark sphere no wider than a city. That is a stellar mass black hole. That is the smallest kind we know, and it is where the whole staircase begins. Tonight we're going to meet the first black hole humanity ever accepted. It was found almost by accident, and it started with a rocket. In 1964, a small suborbital rocket carried a set of Geiger counters up above the atmosphere for just a few minutes. It was hunting for X-rays. The atmosphere blocks them, so you cannot see them from the ground. In the constellation Cygnus, the Swan, the instruments picked up a fierce source of X-rays. They named it Cygnus X1, the first strong X-ray source found in that patch of sky. For years, nobody knew quite what it was. Something in that direction was pouring out X-rays with tremendous power, but the source itself was invisible in ordinary light. Slowly the picture came together. There was a blue supergiant star there, a giant more than 40 times the mass of our Sun. And it was orbiting something it could not see, something compact and heavy and dark. It was pulling gas off the giant star and heating it to millions of degrees as it spiraled inward. That heated gas was the source of the X-rays. The dark companion was a black hole. Today we estimate the Cygnus X1 black hole at about 21 times the mass of our Sun. 21 solar masses orbiting a supergiant more than 40. It sits several thousand light-years away, quietly feeding on its companion. It has done so for as long as we have been watching. Up close, it would be one of the strangest sights in nature. A perfectly black sphere no wider than a mid-sized city, hanging in space, utterly silent, bending the blue light of its giant companion around itself into a warped and glowing halo. There is a story tucked inside this discovery that says something about how science actually works. In 1975, Stephen Hawking made a bet with his friend and fellow physicist Kip Thorne. Hawking bet that Cygnus X1 was not a black hole at all. This was strange, because Hawking had spent years of his life building the theory of black holes. But that was exactly the point. He explained it as an insurance policy. Say black holes turned out not to exist. His life's work would be in ruins, but at least he would win the bet and get some small consolation. If they did exist, he lost the bet, but his work stood. He hedged against his own genius. In 1990, with the evidence grown overwhelming, Hawking conceded. He had lost. Cygnus X1 was a black hole, and the theory had held. So that is the bottom of the staircase. Black holes from 5 to 70 solar masses, born from dying stars, dark and compact and no wider than a city. We can find them by the X-rays they make when they feed. We can find them now by the ripples they send through space when two of them collide. We have found many. This part of the map is filled in. There is a hard ceiling on how big one of these star-born black holes can be. It comes from a piece of physics with a beautifully violent name. It is called the pair instability supernova. It carves a natural boundary into the universe. When a star is truly enormous, tens of times the mass of our Sun, its core burns hotter than anything you can easily imagine. At a certain temperature, the light inside the core becomes strange. It starts spontaneously turning into pairs of particles, matter and antimatter, flashing into existence out of pure radiation. That sounds abstract, but the effect is catastrophic. Every time light converts into a pair of particles, it stops pushing outward. The pressure holding the star up sags. Gravity presses in harder. The core contracts and heats further. That makes even more pairs, which weakens the pressure even more. The star falls into a runaway. The core ignites its oxygen all at once in a single colossal thermonuclear detonation, and the entire star, the whole thing, blows itself completely to pieces. No collapse, no remnant, no black hole at all, just an expanding cloud of debris where a giant star used to be. The universe simply erases these stars, and that is why there is a ceiling. Above a certain birth mass, a star cannot leave a black hole behind, because it detonates entirely before it can. It blows itself to pieces with nothing left at the centre. Exactly where that ceiling sits is one of the genuinely unsettled questions in the field. It is worth being honest about it. Solar masses for the heaviest black hole a dying star could produce directly. But the number keeps moving. The latest analyses from 2025 and 2026 put the lower edge of the forbidden zone somewhere closer to 44 solar masses. Other studies allow it to drift as high as 64. It depends on assumptions about how fast the star spins and what elements it was made of. The exact boundary shifts with each new paper. What does not shift is the basic idea. There is a range of masses where black holes should not be able to form from single stars at all. A forbidden gap etched into nature by the physics of exploding stars. Hold that thought, the forbidden gap, because it comes back later in a way that should genuinely surprise you. Tonight we're going to travel now to the other end of the staircase, the top. Here live the monsters. At the centre of nearly every large galaxy sits a supermassive black hole. Not a few dozen solar masses, not a few hundred. These weigh from around 100,000 solar masses at the small end up to tens of billions at the largest. Our own galaxy has one. It is called Sagittarius A star. It lives at the centre of the Milky Way, about 26,000 light-years from where you are sitting right now. Sagittarius A star weighs about 4.3 million times the mass of our Sun. Sit with that number for a moment. 4.3 million suns, all crushed into a single point of no return. Its event horizon is roughly 27 million miles across. That is wide enough to swallow the entire orbit of the planet Mercury and still have room to spare. An object you could pour our inner solar system into, sitting quietly at the heart of our galaxy. And it makes no sound at all, because sound cannot travel through the vacuum of space. It is enormous, and it is silent. We have actually seen it. In recent years, an effort called the Event Horizon Telescope managed to capture an image of Sagittarius A star, not the black hole itself, which is by definition invisible. Instead, the glowing ring of superheated material swirling just outside the event horizon, wrapped around a dark central shadow. To do it, they linked radio telescopes across the entire planet into one virtual instrument nearly the size of Earth. The resolution required was staggering. Astronomers compared it to standing on Earth and photographing a donut sitting on the surface of the moon, and it worked. We now have a portrait of the shadow at the heart of our galaxy. The image was not how we first learned Sagittarius A star was there. That number, 4.3 million solar masses, was measured a different way. The story of it is worth telling slowly. For decades, two teams of astronomers watched a small handful of stars orbiting the exact centre of the galaxy, not from a single night, but across nearly 30 years. They tracked one star in particular, a star known as S2. It swung around the invisible centre on a long looping orbit. S2 whips around that centre once every 16 years. At its closest approach, it races along at more than 11 million miles per hour. Nothing but an enormous, compact, invisible mass could bend a star into an orbit that tight, and that fast. From the shape and speed of that orbit alone, the teams weighed the dark object. 4.3 million suns, packed into a space smaller than our solar system. There is nothing that can be except a black hole. In 2020, that patient work earned the two team leaders a Nobel Prize. It was the proof that a supermassive black hole anchors our galaxy's core. You should hold on to that method. It is exactly the same method, watching stars swing around an invisible centre, that would later be turned on the hunt for the missing middleweights, in a cluster far closer to home. So there is the top of the staircase. Supermassive black holes, from 100,000 to tens of billions of solar masses, sitting at the cores of galaxies, some of them wide enough to hold a solar system inside their event horizon. This part of the map is filled in too. We can weigh them by watching how fast stars whip around them. We have photographed the shadow of the nearest one. 4.3 million suns sounds like the outer edge of the possible. It is not even close. Sagittarius A star is, by the standards of supermassive black holes, a rather modest example. The largest ones known are almost impossible to hold in the mind. Consider the black hole at the centre of the galaxy M87, the one whose shadow was the very first ever photographed. It weighs roughly 6.5 billion solar masses, not million, billion. Its event horizon is wider than our entire solar system, wide enough to swallow the orbit of Neptune many times over. And even that is not the ceiling. Some galaxies at the hearts of great clusters harbour black holes estimated at tens of billions of solar masses. A handful of candidates push toward 40 billion suns or beyond. They are so large that light would take days just to cross the width of their event horizons. Picture that for a moment. A single dark object so vast that a beam of light, the fastest thing in the universe, would need the better part of a week merely to travel from one side of its shadow to the other. These are the true monsters, the upper end of everything. They anchor the top of our staircase as firmly as the little city-sized black holes anchor the bottom. Between those two extremes, a black hole the size of a town and a black hole the size of a solar system lies the gap. That is what makes it so strange. And now you can see the shape of the problem. On one side, black holes from 5 to 70 solar masses, born from single stars. On the other side, black holes from 100,000 to tens of billions sitting at galactic centres. Between roughly 100 and 100,000 solar masses stretches a near-total void, a missing middle. For decades, that range produced only disputed candidates, never a confirmed population, never a single object that everyone agreed belonged there. We even have a name for the missing class, ready and waiting, like a chair set at a table for a guest who never arrives. Intermediate mass black holes. In the literature they are shortened to a set of initials, but tonight we will mostly just call them the middleweights. Roughly 100 to 100,000 times the mass of our Sun. Heavier than any dying star could ever leave behind. Far lighter than the giants at galactic centres. Somewhere between a black hole you could fit inside a city and one that could swallow our whole solar system, there is supposed to be an entire class. A class of black holes weighing as much as a small star cluster, and for more than 50 years nobody could prove a single one existed. Try holding the strangeness of that gap in a single image. Imagine an elevator in a very tall building. The ground floor is crowded and busy. It is full of stellar mass black holes, the corpses of ordinary stars 5 to 70 suns each. The top floor is enormous and grand. It is home to the supermassive giants, from 100,000 suns up to tens of billions. You step into the elevator on the ground floor. You press the button for the top. The doors close. But as the elevator rises, you notice something deeply wrong. The panel of buttons has a hole in it. There are no middle floors. The building rises straight from the crowded lobby to the grand penthouse with nothing in between. No offices, no landings, no stairs. It is as if the entire middle of the structure were simply missing. That is the gap in the black hole catalogue. Nearly 3 orders of magnitude from 100 solar masses up to 100,000, with almost nothing solidly confirmed inside it. And here is what makes it feel impossible. In every other part of nature, sizes come in smooth ranges. There are pebbles and boulders and mountains and every size in between. There is no reason the universe should build black holes only very small and very large, and skip the middle entirely. The gap should be full. Something must connect the bottom of the staircase to the top, and for over 50 years that connecting rung has refused to appear. Tonight we're going to trace where the idea came from, because it did not come from nowhere. Astronomers proposed these middleweight black holes on paper long before anyone had a way to look for them. The earliest serious suggestions trace back to the early 1970s. They appear in work by researchers like Willer in 1970, and Bärkal and Ostreicher in 1975, and Frank and Rees in 1976. They predicted the missing class decades before any observation could test the prediction. The theory said the middleweights should be out there. The sky, so far, has refused to confirm it cleanly. By the end of tonight, you will understand why the hunt for these objects has become one of the most stubborn and fascinating chases in all of astronomy, and you will understand why the newest telescope ever launched has both strengthened the case and made it more complicated at the same time. To understand why anyone cares so much about a missing size of black hole, you have to understand what the gap would explain if we could fill it, and that takes us to one of the deepest puzzles in the universe, the problem of the very first monsters. Tonight we're going to sit with the deepest puzzle of all, the problem of the very first monsters. When the newest Great Space Telescope, the James Webb, turned its infrared eyes on the most distant, earliest galaxies it could reach, it found something that should not have been possible. It found fully grown, supermassive black holes that had no business existing yet, actively feeding black holes glowing as they devoured gas, in galaxies that existed when the universe was astonishingly young. UHZ-1 is not alone in this. Before James Webb, astronomers using ground telescopes had already found a scattering of impossibly early giants, the brightest black holes in the universe, called quasars. A quasar is a supermassive black hole feeding so violently that the superheated gas around it outshines its entire host galaxy, a beacon visible clear across the cosmos, and some of these beacons come from staggeringly far back in time. One famous quasar shines to us from when the universe was only about 690 million years old. Its black hole already weighs around 800 million suns. Another, found more recently, dates to barely 670 million years after the Big Bang. It carries a black hole of over 1 billion solar masses already assembled, 1 billion suns fully grown when the universe was less than 5% of its current age. James Webb has only sharpened the problem. It has reached further back, finding feeding black holes even earlier, even more overgrown for their surroundings. Each of these objects is a small crisis for our theories. 1 billion solar mass black hole does not appear from nothing. It has to be grown from a seed by feeding over time. And the universe, that early, had barely had time to make its first stars, let alone grow their corpses into billion solar mass monsters. Every one of these early quasars is a clock that seems to have run impossibly fast. And the more of them we find, the louder the same question becomes. What could the seed have possibly been? Consider one particular galaxy, catalogued with the plain name UHZ-1. We are seeing it as it was roughly 470 million years after the Big Bang. To put that in scale, the universe today is about 13.8 billion years old. 470 million years is barely 3% of the current age of everything. We are looking at the universe in its infancy. We see the light that left this galaxy when the cosmos was a small child, and there, in that infant galaxy, sits a black hole, already weighing around 40 million times the mass of our Sun. That number was pieced together carefully. Astronomers combined X-ray data from the Chandra Observatory with infrared data from James Webb and announced the result in November 2023, 40 million solar masses. And here is what made it extraordinary. That black hole was comparable to, or even heavier than, the entire mass of all the stars in its host galaxy combined. The black hole and the starlight weighed roughly the same. Stop and feel how wrong that is. In the universe around us today, the black hole at a galaxy's centre is a tiny fraction of the whole. Our own Sagittarius A star, at 4.3 million solar masses, is well under 1% of the Milky Way's total mass. The galaxy is enormous, and the black hole at its heart, though monstrous by human standards, is a speck by comparison. That is the normal ratio. The galaxy dwarfs its black hole by a factor of thousands. But in UHZ-1, that ratio is upside down. The black hole nearly matches the entire galaxy. It is as if a city's downtown core outweighed every suburb combined. The early universe seems to have built these objects backwards. Monster first, galaxy second. And that is a very hard thing to explain. Here is why it is hard. Imagine you want to grow a supermassive black hole. You have to start with a seed, a smaller black hole, and then feed it, letting it swallow gas over time until it grows huge. The obvious seed would be a stellar mass black hole, the corpse of one of the very first stars. Call it a light seed, somewhere between 10 and 100 solar masses. Now do the math. You need to grow that light seed from 100 solar masses up to 1 billion or more. And you need to do it in under 1 billion years, because that is all the time there was. That turns out to be almost impossibly fast. There is a natural speed limit on how quickly a black hole can feed, called the Eddington limit. Feed too fast, and the intense radiation from the infilling gas actually blows the rest of the gas away. It chokes off the black hole's own meal. It is a kind of built-in brake. To grow a light seed into 1 billion solar mass giant in under 1 billion years, you would have to feed at or above that limit, continuously, for the entire age of the young universe, without ever pausing. Physicists consider that wildly implausible. The brakes should engage, the black hole should choke, it should not be able to grow that fast. It is worth sitting a little longer with why the light seed idea fails, because the failure is what makes everything else necessary. A light seed is the corpse of one of the very first stars, 10 to 100 solar masses. To become 1 billion solar mass quasar, it must multiply its mass by roughly 10 million times, and it has under 1 billion years to do it. The trouble is the Eddington limit, that natural speed brake. A black hole feeding at that limit grows in a very specific way. Its mass can double, but only about every 50 million years or so. Doubling. So count the doublings you need. To go from 100 solar masses to 1 billion is a factor of 10 million. That is a little over 23 doublings. At 50 million years each, 23 doublings would take more than 1 billion years, and that is longer than the entire age of the universe at the time those quasars already existed. The arithmetic simply does not close. Even at full throttle, without a single pause, without ever choking on its own radiation, the black hole could not have doubled enough times in the time available. And in reality, black holes do not feed at full throttle without pause. They flicker. They starve between meals. Their own light blows their food away. So the real growth is slower still. The gap between what the math allows and what we observe only widens. A light seed cannot get you there. The universe needed a bigger head start. So how did the earliest monsters get so big so quickly? This is where the middleweights walk onto the stage, because they may be the answer. The alternative is to start with a bigger seed. Not 100 solar masses, but 10,000. Or 100,000. A heavy seed. Suppose the universe could somehow make black holes that were already the size of a small star cluster right from the start. Then the growth problem eases enormously. You would not need to break the speed limit. You would have a head start of several thousand suns, and a heavy seed of 10,000 to 100,000 solar masses is, by definition, a middleweight. An intermediate mass black hole, the exact missing class. So the question of how the universe's first monsters formed collapses, in part into the question we started with. Where are the middleweights? If they exist as a real population, they are the missing seeds. They are the fossil starting points of every giant black hole at every galaxy's centre. Find them, and you close the loop between how the largest black holes began and what that beginning actually looked like. But how would the universe make a black hole of 10,000 solar masses without a single dying star being big enough to leave one behind? For that, there is a strange and beautiful idea called direct collapse. Picture the very early universe. It is a fog of hydrogen and helium and almost nothing else. The heavier elements, the carbon and oxygen and iron that make up you and the Earth, and everything familiar, had not been forged yet, because forging them requires generations of stars to live and die first. So the early gas was pristine, chemically simple, and that simplicity matters more than you would think, because heavier elements are what allow a gas cloud to cool efficiently. When a normal gas cloud in today's universe collapses, it cools quickly, and as it cools it fragments. It breaks into many separate clumps, and each clump becomes a star. That is why stars are born in families, in clusters, rather than as single enormous objects. The cooling and the fragmenting go together. But in the pristine early universe, without those heavier elements, a giant gas cloud could not cool efficiently. It could not shed its heat and fragment into a family of stars. Instead, imagine a gas cloud larger than our entire solar system. It collapses slowly under its own weight, growing hotter and denser, but unable to break apart. It contracts as a single unit, and when a cloud that enormous caves in on itself all at once, without ever passing through a normal stellar phase, it can fall directly into a black hole. No star, no supernova, just a giant cloud collapsing straight into a black hole seed of 10,000 to 100,000 solar masses. Direct collapse only works if a very particular set of conditions all line up at once, and that is part of why it is thought to be rare. First, the gas cloud must be almost perfectly pristine. It must be made of nearly pure hydrogen and helium, with essentially none of the heavier elements that would let it cool and fragment into stars. Second, the cloud must be bathed in strong ultraviolet light from nearby young galaxies. That radiation breaks apart the hydrogen molecules that would otherwise help the gas cool. Keep the gas hot, and it cannot break into clumps. Third, the cloud must be massive, tens of thousands to hundreds of thousands of solar masses of gas, all funneling inward together. When those conditions hold, the gas does something almost nothing else in the universe does. It skips the star stage entirely. Instead of fragmenting into a cluster of ordinary stars, the whole cloud collapses as one. It may form a single bloated supermassive star that lives briefly and then falls straight into a black hole of 10,000 to 100,000 solar masses. No supernova, no slow build-up. A heavy seed, born already the size of a small star cluster, ready to grow into a quasar without needing to break the speed limit. It is an elegant solution to the timing problem. It hands the universe a head start of tens of thousands of suns, and it produces, at the moment of its birth, exactly the kind of object we have been calling the missing middleweight. That is direct collapse. And that galaxy we met a moment ago, UHC1, with its impossibly overmassive black hole in the infant universe, is considered the single best piece of observational evidence we have that this actually happens. A light seed simply could not reach 40 million solar masses that early, but a heavy seed, born from direct collapse, could. UHZ1 looks like the smoking gun for the heavy seed pathway. Not proof beyond all doubt, but the strongest hint we have. James Webb has found other strange objects that point the same direction, and they have earned themselves an oddly charming nickname: little red dots. These are extremely compact, extremely red points of light scattered through the early universe. Many astronomers interpret them as compact galaxies hiding over massive, actively feeding black holes at their hearts, wrapped in dust that reddens their light. If that interpretation holds, they are more examples of the early universe building black holes far too big, far too fast, exactly as the heavy seed idea predicts. But here honesty demands a pause, because this is a live debate, not a settled fact. The little red dots are genuinely mysterious, and not everyone agrees they are over-massive black holes at all. Some researchers argue that their extreme red colour could come instead from unusually dense star formation, or from strange geometries of dust, without any dominant black hole doing the work. The question of what the little red dots truly are is being actively fought over in the research literature right now, in 2025 and 2026, with no clean resolution yet, so hold them lightly. They may be another clue pointing toward the missing middleweights. They may turn out to be something else entirely. The uncertainty is part of the story. It is worth understanding just how the little red dots feed this whole debate, because they are one of James Webb's genuine surprises. Nobody predicted them. When the telescope began imaging the deep early universe, it kept turning up these tiny, intensely red points of light. Far more of them than anyone expected. They were so common in the infant cosmos that they seem to have been a normal feature of that era, and then largely vanished. Their light suggests two things fighting for the same space. The red colour and compactness hint at a small dense object, and in many of them, the light carries the signature of gas moving at tremendous speeds, thousands of miles per second. exactly what you would expect from gas whipping around a black hole. If that reading is right, these dots are compact early galaxies with overmassive black holes at their cores, feeding hard, cloaked in dust that reddens their glow. And in early 2026, a direct mass measurement of the black hole inside one little red dot was published. It was a landmark because it moved the interpretation from inference toward measurement. But the caution remains real. Some researchers argue the same red light could come from dense knots of star formation or from unusual dust with no dominant black hole at all. And some 2026 work even argues the dots are best explained as direct collapse black holes themselves, tying them directly to the heavy seed story. So the little red dots sit right at the centre of the seed problem, pulling in every direction at once, unresolved, and all the more fascinating for it. What all of this establishes is why the gap matters so much. If intermediate mass black holes are real and common, they explain the impossible early monsters. They are the seeds. They are the missing first chapter of every giant black hole's life, which means the hunt for them is not some minor bookkeeping exercise. It is a hunt for the origin of the largest objects in the universe. And the best place to start that hunt turned out to be surprisingly close to home. Tonight we're going to visit a fuzzy point of light in the southern sky. Humans have been looking at it for as long as we have looked up at all. To the naked eye from the southern hemisphere, it appears as a faint smudge. For most of history, people thought it was just an ordinary star. It even got a star's name, but it is not a star. When telescopes finally resolved it, they revealed something else. This single faint point is actually a swarm of roughly 10 million stars packed together into a ball. It is called Omega Centauri. It is the largest and brightest globular cluster orbiting our galaxy. Omega Centauri is worth knowing on its own terms because it is a genuinely strange object. It is the largest globular cluster orbiting our galaxy, and by a wide margin. A typical globular cluster holds a few 100,000 stars. Omega Centauri holds roughly 10 million, packed into that ball about 150 light-years wide. It is bright enough to have been catalogued as a single star in ancient times. It carries a star's designation to this day, even though it is nothing of the sort. But the deepest strangeness is in its stars themselves. An ordinary globular cluster is made of stars that all formed at roughly the same time, from the same cloud, with the same chemical makeup. Like a single family born on a single day. Omega Centauri is not like that. Its stars come in multiple distinct populations, born at different times, with different chemical fingerprints. It is as if several separate families had been folded together into one crowd. That is a powerful clue. It suggests Omega Centauri is not a true globular cluster at all. Instead, it may be the surviving core of a small dwarf galaxy. A galaxy that once orbited the Milky Way independently, with its own history of star formation. Then our galaxy captured it, and stripped away its outer stars over billions of years. What is left is the dense, ancient heart of a devoured galaxy. And a devoured galaxy might well have kept the black hole that once sat at its own centre. That single idea is what makes it such a promising place to hunt. Omega Centauri sits about 17,700 light-years from Earth. Hold that number against something we said earlier, the supermassive black hole at the centre of our own galaxy, Sagittarius A star, is 26,000 light-years away. So this globular cluster is actually closer to you right now than the black hole at the heart of the Milky Way, and it may hold the best candidate for a middleweight black hole anywhere in the universe. 10 million stars is a difficult number to feel. Let this help. Those stars are packed into a sphere about 150 light-years across, which sounds roomy until you realize how many stars are inside it. Near the crowded core of the cluster, stars sit thousands of times more densely than they do in our own quiet corner of the galaxy. If you stood on a hypothetical planet somewhere inside that core and looked up, the sky would blaze. Thousands of stars brighter than Venus scattered edge to edge. So many and so bright that true darkness might never fully arrive. a perpetual soft twilight made entirely of suns. Astronomers had a reason to suspect a black hole might lurk at the centre of this swarm. Omega Centauri is now thought to be the stripped-down core of a small galaxy, a dwarf galaxy that once orbited the Milky Way on its own. Then our galaxy's gravity slowly tore away its outer stars over billions of years, leaving only the dense central knot behind. And if it was once a real galaxy with its own nucleus, it might well have kept a black hole from those days, a central black hole orphaned, still sitting in the heart of what remains, exactly the kind of place a middleweight could hide. So astronomers went looking, and the way they looked is remarkable. They could not see the black hole. If it is there, it makes no light of its own. So instead they watched the stars. In a study published in July 2024, a team analysed more than 500 images of Omega Centauri. They were taken by the Hubble Space Telescope across 2 decades, 20 years of watching the same cluster. From those images, they tracked the individual motions of 1.4 million stars. They measured how each one drifted year by year across the sky. They were doing something you could fairly call stellar forensics. And in the crowded core, they found 7 stars behaving impossibly. 7 stars moving so fast that they should have been flung clean out of the cluster and lost to space entirely. The gravity of the ordinary stars around them was nowhere near enough to hold them. And yet there they were, still bound, still swinging around the centre, held in place by something invisible. Think of it this way. Imagine watching 7 grains of sand whirling around the edge of a whirlpool, faster than any current you can see should allow. And you cannot make out the drain at the centre. You cannot see the drain, but you can measure how fast the sand is moving. From that speed alone, you can work out how strong the pull at the centre must be. That is exactly what the Hubble team did. From the speed of those 7 fleeing stars, they calculated how much invisible mass had to sit at the centre to hold them. The heart of the argument is a simple idea called escape velocity. Every gathering of mass has a speed above which an object can break free of its gravity forever. Throw a ball hard enough and it never comes back down. A star cluster is the same. Move faster than the cluster's escape velocity, and you sail out into intergalactic space and never return. Now here is the crux. The 7 stars in Omega Centauri's crowded core were clocked above the escape speed that every visible star in the cluster added together could enforce. By the ordinary reckoning of the cluster's visible mass, those 7 stars should already be gone, flung out, lost to the dark between galaxies. And yet, across 2 decades of Hubble images, they were still there, still circling the centre, plainly still bound to something. There is only one clean way to explain that. There must be extra mass at the centre that we cannot see. Enough extra gravity to raise the escape velocity above the speed of those 7 stars. Enough to hold on to runaways that the visible stars alone could never hold. Something invisible and heavy, sitting right at the core doing the holding. The faster the trapped stars move, the more invisible mass it takes to keep them. Measure their speeds, add up the visible stars, and whatever is left over is the mass of the unseen thing. That subtraction is what pointed, for the first time in the nearest great cluster, straight at a middleweight black hole. The answer pointed straight at a middleweight black hole. The plausible mass range from that study came out around 39,000 to 47,000 solar masses, with an extreme lower limit, the smallest thing that could possibly do the job of about 8,200 solar masses. Either way, well inside the intermediate range. A black hole heavier than any dying star could leave, far lighter than a galactic giant, sitting quietly at the centre of the nearest great star cluster, holding 7 runaway stars on invisible leashes. It was, and is, the strongest and closest candidate for the missing class of black holes we have ever found. But notice the word candidate, because the story does not end with a clean confirmation. It ends so far with more questions. Here is the first problem. The 7 fast stars tell you there is mass at the centre. They do not tell you what shape that mass takes, a single intermediate mass black hole of 40,000 suns would produce exactly that gravitational signature. But so would something else. A tight cluster of many smaller black holes, ordinary stellar mass black holes, hundreds of them crowded together in the core. Together they could add up to the same total mass and pull on those 7 stars the same way. From the outside, from the motion of the stars alone, the two possibilities can look nearly identical. One middleweight, or a swarm of lightweights. The stellar motions cannot easily tell them apart. And that alternative, a hidden crowd of small black holes rather than one big one, remains genuinely on the table. The swarm of small black holes objection deserves to be taken seriously, because it is not easy to rule out, and honesty about it is the whole point. Over its long life, a cluster like Omega Centauri would have produced many stellar mass black holes, the corpses of its heaviest stars. Those black holes, being heavy, tend to sink toward the centre over time and gather there. So a dense knot of ordinary black holes at the core is not some exotic invention. It is expected. And a tight enough knot of them could add up to the same tens of thousands of solar masses that the fast stars require. It would pull on those stars in nearly the same way as a single big black hole would. From the stellar motions alone, the two pictures blur together. There have been other ways to probe it. Some astronomers have looked for the faint radio whisper a feeding black hole might give off. Others have looked for the timing signals of pulsars, dead spinning stars whose ticks could be nudged by a central mass. So far, none of these has delivered a clean, decisive answer. And the mass estimates themselves keep sliding depending on which method and which assumptions you use, from as low as 8,000 suns to as high as nearly 50,000. That is not a sign of sloppiness. It is a sign of a genuinely hard measurement, made near the limit of what current instruments can do, on an object that gives off no light of its own. The central mass is almost certainly real. Whether it is one middleweight or a crowd of lightweights is still, honestly, undecided, so astronomers wanted a second independent way to check. And that is where the newest telescope came in. Tonight we're going to watch what happened when the newest telescope tried to confirm it. In December 2025, a team using the James Webb Space Telescope, led by a researcher named Stephen Chen, turned its infrared instruments on the centre of Omega Centauri. Their idea was clever. Say there really is a black hole there, and it is feeding at all, even slowly, on the thin gas drifting through the cluster's core. Then the infalling gas should glow. It should heat up as it spirals in and give off a faint but detectable infrared signature. Find that glow, and you would have a second independent confirmation, a direct sign of the black hole itself rather than just its gravity. They looked with the sharpest infrared eyes ever built, and they found nothing. No strong accretion glow, no clear sign of gas feeding a central engine. Silence. Now, that sounds like a defeat, but it is subtler than that, and this is where the honesty of the hunt really matters. A non-detection does not mean the black hole is not there. It means that if it is there, it is essentially starving, not feeding enough to glow. A black hole that is not accreting does not shine, does not flare in X-rays, does not announce itself in any visible way at all. It becomes a truly silent void, a dark drain in a shooting gallery of 1,000,000 stars, detectable only through its gravity's fingerprints on its neighbours, exactly the fingerprints Hubble had already found. The lead researcher put it plainly. Despite the unprecedented depth and resolution James Webb offers, he noted, searching for these black hole signals in such incredibly crowded environments remains genuinely challenging. The telescope did its job perfectly. The environment is just very hard. And the non-detection did something interesting to the numbers. To fit the fact that no glow appeared, the mass estimate had to shift again. The James Webb constraint pushed the figure to around 20,000 solar masses, and it excluded that earlier extreme lower limit of 8,200 are simply too small to be consistent with everything else. So watch what has happened to this single object over time. The estimated mass has wandered from 8,200 to a plausible range of 39 to 47,000, to a revised figure near 20,000. 3 different studies, 3 different methods, 3 different numbers, all for the same invisible thing at the centre of the same cluster. That is not a scandal. That is what an honest hunt looks like when the quarry refuses to be seen. Every number is a genuine attempt, and every number shifts as new information arrives. What has not changed across all of it is the core finding. Something heavy and invisible sits at the centre of Omega Centauri in the intermediate range, holding fast stars in place. What it is exactly, one middleweight or a swarm of smaller ones, and precisely how heavy it is, remain open. The best candidate in the sky is still, after all this, a candidate. So what would finally settle it, one way or the other? The answer is patience and sharper eyes, and both are coming. The core method is what astronomers call proper motion, the slow drift of individual stars across the sky, measured by comparing images taken years apart. The longer the baseline, the more precisely you can trace each star's path, and the tighter you can pin the mass at the centre. The Omega Centauri result already rests on 2 decades of Hubble images. Extend that baseline by another 10 or 20 years, adding fresh images to the pile, and the orbits of those fast central stars sharpen dramatically. A single star seen curving on a closed path around the very centre, the way S2 curves around the black hole in our own galaxy, would be close to decisive. Next-generation instruments will help enormously. Giant ground telescopes now being built with mirrors over 100 feet across should be able to resolve individual stellar motions in that crowded core far more finely than Hubble ever could. Deeper infrared searches with James Webb may yet catch the faint accretion glow that has so far stayed just out of reach, and a swarm of small black holes and a single big one are so hard to tell apart today. But they leave subtly different fingerprints in the detailed distribution of stellar speeds, fingerprints that better data can eventually separate. None of this is fast. It is measured in decades, not headlines. But the trend is clear. The nearest candidate is not going anywhere, and our ability to weigh it is only getting better. The nearest, strongest case for the missing black hole in the entire universe sits closer to Earth than the giant anchored at the middle of the Milky Way. It has been hiding in plain sight inside a naked-eye star cluster for as long as humans have looked up, and it still refuses to reveal itself directly. If that does not deepen the mystery, nothing will. Omega Centauri is the closest candidate. It is not the only one. Tonight we're going to meet a few more of them, scattered across very different distances and found by very different means. The hunt for the middleweights has been running for decades on several fronts at once. Each front has produced its own strange, half-glimpsed object. To really appreciate how these things hide, you have to see them for yourself. Start with an object called HLX-1. The name is a compression of hyperluminous X-ray source 1, and it lives in the outskirts of a galaxy called ESO 24349, about 290 million light-years from Earth. It was first spotted in November 2004, and for a long time it has held the title of the single, strongest middleweight candidate found through X-rays. What made HLX-1 stand out was simply how bright it was. Far too bright. Its X-ray output ran at a staggering rate, roughly 100 times brighter than the theoretical maximum an ordinary stellar mass black hole should be able to reach, even when feeding at full throttle. Remember the Eddington limit, the natural break on how fast a black hole can feed. A small stellar mass black hole running flat out has a ceiling on how bright it can get. HLX-1 blew past that ceiling by a factor of 100. There are only so many ways to explain that. The cleanest one is that the black hole is simply much heavier than a stellar mass object. A bigger black hole has a higher ceiling. Do the math backward from the brightness, and you land at an estimated mass of around 20,000 solar masses, squarely in the intermediate range. Where did such an object come from? sitting all alone in a galaxy's outer suburbs rather than at its centre. The leading explanation echoes what we saw with Omega Centauri. HLX-1 is thought to be the stripped nucleus of a small dwarf galaxy. It collided with the larger ESO 24349 and was mostly torn apart. What survived was its dense central core, and the black hole that once sat at that core now exposed and orbiting out in the halo of the big galaxy. A middleweight, left behind like a pit after the fruit around it was eaten away. What makes HLX-1 more than a bright dot is how it behaves over time, and the behaviour reads like a black hole's own diary. Astronomers watched it for years, and it did not simply shine steadily. It flared and dimmed in a pattern, brightening dramatically and then fading, roughly on a repeating cycle. A pattern like that hints at an orbit. The best reading is that HLX-1 has a companion, perhaps a star, swinging past it on a stretched looping path. Each time the companion draws close, it spills a fresh meal of gas onto the black hole, which flares up as it feeds. Feed, fade, wait, feed again. And crucially, astronomers studied the details of that feeding, the way the X-ray spectrum shifted between bright and faint states. The numbers behaved exactly the way a heavy black hole should, and not at all the way a light one would. The transitions between states, the temperatures of the infalling gas, the shape of the glow, all scaled with a mass of around 20,000 suns. So it is not one measurement standing alone. It is a whole consistent story. An object in a galaxy's outer suburbs, far too bright to be an ordinary stellar black hole, flaring on a schedule that suggests a feeding orbit, with spectral behaviour that matches a middleweight at every turn. That accumulation is why HLX-1 held the crown as the strongest X-ray candidate for so many years, and still, we have never seen the black hole. We have only watched it eat, over and over, and inferred its weight from its appetite. If HLX-1's brightness translated into ordinary visible light, it would be a genuinely dazzling thing, a single point in a galaxy's outskirts, briefly outshining the combined light of every ordinary black hole binary in that whole galaxy. And yet, once again, it is a candidate, a very strong one, arguably the best X-ray case there is. But the exact mass and nature still carry uncertainty. We are always reasoning backward from indirect light, never looking at the black hole itself. Tonight we're going to turn to the candidate that comes closest to an actual birth certificate. It did not arrive as light at all. It arrived as a tremor in the shape of space. On May 21st, 2019, the great gravitational-wave detectors on Earth, the instruments called LIGO and Virgo, recorded a signal. Gravitational waves are ripples in the fabric of space-time itself, produced when very massive objects accelerate violently. They had been detected before from merging black holes and neutron stars, but this signal, catalogued as JWST9052b, was special. It was the sound, if you can call it that, of two black holes spiralling together and merging into one, and the masses involved changed everything. The two black holes that collided weighed about 85 and about 66 solar masses. They spiraled inward, faster and faster. In a final fraction of a second, they merged into a single black hole of about 142 solar masses, and in that instant of merging, roughly 8 solar masses worth of material was converted directly into the energy of gravitational waves. It was radiated away as a tremor through the whole universe in less than a second. 8 entire suns erased into pure ripples in space in the blink of an eye. Look at that final number. 142 solar masses, that is above 100. It lands for the first time with a firm and secure measurement inside the intermediate range. One member of the Discovery team described it as the first and only firm, secure mass measurement of an intermediate mass black hole, caught at the very moment of its birth. Not inferred from a swarm of stars, not reasoned backward from X-ray brightness. Directly measured from the ripple the birth itself sent out. The event was announced to the world on September 2nd, 2020. But the real shock is in the two black holes that went in, not the one that came out. Remember the forbidden gap. Remember the pair instability physics that says a dying star cannot leave behind a black hole in a certain mass range because it detonates completely instead. The two black holes that merged here, at 85 and 66 solar masses, sit inside or above that forbidden zone, which means neither of them should have been able to form from a single collapsing star in the first place. They should not exist. And yet they collided. So how did they get there? The leading explanation is one of the most striking ideas in the whole field. It says these black holes were not born from single stars at all. They were themselves the products of earlier mergers. Somewhere in a dense, crowded environment, a place packed with black holes, small black holes merged into bigger ones, and those bigger ones merged again and again, each generation stacking mass on top of the last. Astrophysicists sometimes describe it, half grimly, as black holes eating their own kind, merger upon merger, in the dark, until a black hole climbs up out of the forbidden gap and into the intermediate range through sheer repetition. This is called hierarchical merging. It is a cosmic snowball effect that runs entirely in silence. Its only trace is a ripple in space-time lasting a fraction of a second. There is a detail here worth pausing on, because it shows how faint these signals truly are. When the gravitational waves from JWST 521 washed across the Earth, they stretched and compressed space itself as they passed. That is what a gravitational wave does. It changes distances, but the effect was unbelievably tiny. Even at its peak, it altered the distance between the detector's mirrors by less than the width of a single proton. We built machines sensitive enough to feel a change smaller than a proton spread across miles of laser beam, all to hear two black holes collide a great distance away. That we can detect this at all is one of the quiet miracles of modern physics. It is worth understanding what the detectors actually recorded, because the signal itself is a small marvel. As two black holes spiral toward each other, they orbit faster and faster, and they radiate gravitational waves at a rising frequency. Translate that rising frequency into sound, and it becomes a short upward sweep, a rising tone that astronomers affectionately call a chirp. Most black hole mergers detected so far produce a chirp lasting a fraction of a second, sweeping up in pitch as the two objects circle in. But JW19045121 was different, and its difference was the whole story. Because the two black holes were so heavy, they were already moving slowly. They were already close to merging by the time their signal entered the detector's range, so there was barely any chirp at all. Instead of a rising sweep, the instruments caught something more like a single low thud, a brief bang, over almost as soon as it began. That short, deep bang was the signature of unusually massive objects. It was the first clue that something out of the ordinary had happened. And when the analysis came back, the reason for the strangeness was clear. The two black holes weighed 85 and 66 solar masses. Both sit inside or above the forbidden pair instability gap, the range where a dying star cannot leave a remnant at all, because it detonates completely instead. Neither black hole should have been born from a single star. The detectors had caught the collision of two objects that stellar physics says should not exist, merging into a third that finally landed in the missing middle. There is a loose thread on this story, and honesty requires that we name it. Around the same time and in roughly the same patch of sky as JWST 190521, a separate survey called the Zwicky Transient Facility reported a possible flash of ordinary light. If that flash were truly connected to the black hole merger, it would be the first time in history we ever caught visible light from two black holes colliding. That would be a genuinely enormous result, because merging black holes are not supposed to produce any light at all. But that connection remains unconfirmed and contested. Much of the community treats it as a likely coincidence, two unrelated events that happen to land near each other, so set it aside as an unresolved possibility. an intriguing maybe rather than a fact. There is one more contested detail on GW190521 worth knowing. Some later reanalyses of the signal suggest the two black holes were not spiralling together in a neat circle, but on a stretched eccentric orbit, with an eccentricity estimate as high as 0.67. If true, that points toward formation in a dense, crowded stellar environment, a globular cluster or a galactic nucleus, rather than an isolated pair of stars quietly evolving together. That would fit the hierarchical merger picture beautifully. But the original discovery analysis assumed a simpler, more circular in spiral, and the eccentric interpretation is not universally accepted. Another honest maybe, another place where the same data supports more than one story. The gravitational wave hunt gave us that one firm middleweight, born in a tremor, and James Webb has recently added a whole new category of candidate, out in small galaxies, that both excites and cautions the field in equal measure. In March 2026, researchers using James Webb reported finding dwarf galaxies at middle distances across cosmic time. Their central black holes make up as much as 60% of their entire host galaxy's mass. 60%. Recall that in nearby, present-day galaxies, the central black hole is typically something like 0.1% to 0.5% of the galaxy. These distant dwarfs are wildly out of proportion. Their black holes are swollen to a size that dwarfs everything around them. Another echo of the overmassive puzzle we met in the early universe. If those black holes are real, some of them may well sit in the intermediate range. More relics of the seed population we are hunting for. Dwarf galaxies have quietly become one of the most promising hunting grounds in this whole search, and it is worth understanding why. A dwarf galaxy is a small galaxy, sometimes only a few 100 million stars or fewer, far smaller than the Milky Way's hundreds of billions. And here is the key idea. Big galaxies have violent histories. They grow by swallowing smaller galaxies, and each merger can grow and disturb their central black holes. Dwarf galaxies, especially quiet, undisturbed ones, may have escaped much of that churning. So the black hole at the centre of a small, calm dwarf galaxy may still be close to its original seed size, never having grown into a giant. If seeds are middleweights, then dwarf galaxy centres are exactly where surviving middleweights should hide. That is why astronomers have turned James Webb spectrographs on dwarf galaxy after dwarf galaxy. They spread the central light into its component colours and hunt for the specific emission lines that betray gas whirling around a black hole. And the campaigns have found candidates, small galaxies whose cores show the telltale fast-moving gas and high-energy glow of an active black hole in the intermediate range. Each confirmed one is a small triumph, a middleweight caught not by a merger or a shredded star, but simply sitting at the heart of a quiet little galaxy, feeding gently. If these hold up as a real population, they may be the closest thing to the fossil seeds we could ever hope to find. The original starting points, preserved almost unchanged, in galaxies too small to have grown their black holes into monsters. But here comes the caution, and it arrived in the same year from a companion study, and it is exactly the kind of check that keeps this science honest. A separate 2026 investigation looked at nearby small galaxies that had the same telltale infrared colours, the colours usually taken as a sign of an actively feeding black hole. And when researchers examined those galaxies more carefully, with spectroscopy, some of them showed no actual sign of a black hole feeding at all. What looked like the glow of an accreting black hole turned out in some cases to be a compact burst of intense star formation instead, a nuclear starburst, wearing the disguise of an active black hole. Same colours, different cores. That is a genuinely important warning. It means some of the candidates found by their colours alone may not be black holes at all, and it forces a discipline onto the whole enterprise. You cannot simply count red or infrared bright dwarf galaxies and declare a new population of middleweights. You have to check each one, and some will fall away as imposters. How many of the exciting new dwarf galaxy candidates are real black holes, and how many are starbursts in costume is an open question being sorted out right now. If you ask which single candidate looks strongest as of right now, the honest answer is that it depends on what you mean by strong, and no one of them is clean. For a firm direct mass measurement, GW190521 still stands alone. Announced in September 2020, it remains the only object with a secure directly weighed mass. 142 solar masses sitting unambiguously in the intermediate range, measured from the pure gravity of its birth with nothing in between. Nothing else comes close on that front. For the strongest case for a middleweight quietly living in a real present-day system, Omega Centauri holds the position. It was refined again by James Webb in December 2025, though still tangled in the swarm versus single debate. For a middleweight caught actively destroying a star in real time, EP24022222R, caught in March 2024, is the freshest and best. And for the newest frontier, the dwarf galaxy black holes reported through 2026 are the most exciting and the most fragile. Some fraction of them will surely turn out to be imposters, so there is no single winner. There is a scatter of strong candidates, each strong in a different way, each carrying its own honest caveat. And that scatter is precisely the state of the field. Not one triumphant detection that ends the argument. Instead, a handful of very good cases pointing from different directions at the same conclusion. This missing class is real. We're closing in on it from several angles at once, without yet having pinned any single example beyond all reasonable dispute. That is where things genuinely stand tonight. So step back and look at the collection we've gathered. A gravitational tremor from a firm 142 solar mass merger, a blazing X-ray source in a distant galaxy's suburbs, pointing to 20,000 suns, a swarm of runaway stars around an invisible centre in the nearest great cluster, a crop of overmassive dwarf galaxy black holes, some of which may be imposters. Every one of them is a genuine candidate. Not one of them is a clean, undisputed, everyone agrees confirmation of the missing class as a common population. The middleweights keep almost appearing and then dissolving back into ambiguity. Which raises a natural question. If these things are so hard to see, is there any method that reliably drags one out of hiding? As it turns out, there may be. It is one of the most dramatic events in nature. To find a black hole that gives off no light of its own, you need it to do something. And the most spectacular thing a quiet black hole can do is catch a passing star and tear it apart. This is called a tidal disruption event, and the physics behind it is simpler than it sounds. Gravity gets stronger the closer you are to a mass, so when a star wanders too close to a black hole, the black hole's gravity pulls harder on the near side of the star than on the far side. If the star gets close enough, that difference in pull becomes overwhelming. The near side is yanked inward far more forcefully than the far side, and the star is stretched, first into an elongated teardrop, then into a long, thin, glowing filament. Astronomers have a wonderfully vivid nickname for this stretching. They call it spaghettification. The star is pulled into stellar noodles. As the shredded star's material streams away, it does not fall straight in. It swirls into a hot, bright disk of debris around the black hole, spiraling inward before it finally crosses the point of no return. And that swirling, heated debris blazes. A tidal disruption event can flare bright enough to briefly outshine an entire galaxy, or rival a supernova. A beacon visible across billions of light years, which is the whole point. The black hole itself is dark and silent and otherwise invisible, but when it shreds a star, it lights a flare that can be seen from clear across the universe. The black hole announces itself through its victim. Picture the full anatomy of one of these events slowly from the star's point of view. For most of its life, the star has orbited at a safe distance, one of many circling a quiet, dark centre. Then, over ages, gravity nudges its orbit inward until on one fatal pass it swings too close. At closest approach, the whole passage lasts only hours. But in those hours, everything changes. The black hole's gravity pulls so much harder on the near face of the star than the far face. So the star is stretched along its length. It is drawn out first into a teardrop, then into a long luminous ribbon of gas, thousands of times longer than the original star. Roughly half of that ribbon is flung outward and lost. The other half falls back toward the black hole, but it cannot dive straight in. It loops around, tangles with itself, and settles into a hot whirling disk. That disk is what blazes. The light does not appear all at once. It rises over weeks or months as the debris circularizes and heats. It peaks. Then it fades slowly over months to years as the black hole swallows the last of its meal. Astronomers call the record of that brightening and fading the light curve, and the shape of the light curve is a code. How fast it rises, how bright it peaks, how long it takes to fade, all of it depends on the mass of the black hole. Read the curve, and you read the weight of the invisible thing that did the shredding. And here is the truly useful part for our hunt. The exact character of that flare, how bright it gets, how quickly it rises, how long it lasts, depends on the mass of the black hole doing the shredding. A tidal disruption event is a natural weighing scale. A smaller black hole shreds and swallows a star faster, producing a shorter, fainter flare. A supermassive giant produces a very different signature. So by studying the shape of the flare, astronomers can estimate the mass of the black hole that caused it, even though they never see the black hole itself. There is an even deeper reason these events are perfect for finding middleweight specifically, and it is a lovely piece of geometry. For a black hole to shred a star rather than simply swallow it whole, the star has to be torn apart outside the event horizon, out where the destruction is visible. For the very largest supermassive black holes, the event horizon is so enormous that a small star can cross it and be swallowed entirely before the tides ever get strong enough to shred it. No flare. The star just vanishes, uneventfully into the dark. But for a middleweight black hole, the tidal disruption happens well outside the horizon, in full view. So tidal disruption events are especially good at catching exactly the intermediate mass range. The middleweights shred their stars where we can watch. The giants often swallow them whole in silence. For years this was mostly theory. Then, in 2024, one arrived, caught in the act. Tonight, we're going to watch it happen. On March 11th, 2024, a satellite called the Einstein probe caught a burst of X-rays from a distant galaxy. It was a wide-field X-ray telescope launched by China only 2 months earlier. It was still in its early commissioning phase, its instruments barely warmed up. The event was catalogued as EP242222, and as astronomers followed up, gathering data across X-ray and optical light and taking spectra, they realized what they were watching. It is now described as the first robust intermediate mass black hole tidal disruption event ever captured in real time. It came with a full suite of follow-up observations and spectroscopic confirmation. 2 details made the case strong. First, the location. The flare came not from the center of its host galaxy, where a supermassive black hole would sit, but from the galaxy's outskirts. That is exactly where you would expect a middleweight to live, off-center, the stripped nucleus of a swallowed satellite galaxy, or the core of a massive dense star cluster, orbiting out in the halo rather than at the bright center. The off-center location itself was a clue that this was not one of the usual galactic giants. That off-center detail is more important than it might first sound, and it has grown into a search strategy all its own. Most tidal disruption events found so far come from the exact centers of galaxies, where the supermassive giants sit. That is expected. But astronomers have begun deliberately hunting for the rare flares that appear off-center, well away from a galaxy's bright nucleus, out in its disk or its halo. An off-center flare is a powerful clue, because a supermassive black hole should not be sitting out there. Something smaller must be, and a middleweight is exactly the kind of black hole expected to live off-centre. It may be the stripped nucleus of a smaller galaxy that was swallowed and dragged inward, or the dense core of a massive star cluster orbiting through the larger galaxy's halo. So when a shredded star flare lights up far from a galaxy's heart, it flags a likely middleweight almost by its location alone before any mass is even measured. Surveys are now being combed specifically for these offset events. It is a clever inversion of the usual approach. Instead of looking where black holes are known to be and asking their size, astronomers look for destruction happening where no giant should be. Then they let the wrongness of the location point them toward the missing class. Each offset flare found is a small map pin dropped on a place where a middleweight may quietly live, revealed only because an unlucky star wandered too close and lit a beacon far from home, out in the lonely suburbs where the giants never reach. Second, the spectrum. When astronomers spread the light out into its component colours, they found the specific fingerprint lines, emission from helium and nitrogen, that mark a genuine tidal disruption event and distinguish it from other kinds of cosmic flare. This was really a star being torn apart, not some other transient masquerading as one. And the way the flare unfolded taught the field something new, something that overturns the picture most people have in their heads. When you imagine a star being eaten by a black hole, you probably imagine violence and speed, an instant, an explosion. But this was the opposite. The models of EP242222A describe a distinctive, slow signature for these middleweight disruptions. A faint, slow-rising early phase in X-rays, building not over seconds but over the order of years. Then a plateau where the brightness levels off near the black hole's own natural brightness limit. Not a bang. More like a candle being slowly smothered and then flaring steadily back up. The star's fatal orbit near the black hole may last only minutes to hours at closest approach, but the glowing aftermath unfolds across years. A slow-motion death, visible from across the universe, triggered by a single unlucky orbit. That slow, distinctive shape is now being used as a template, a pattern to search for in survey data, to pick out more of these middleweight disruptions from the flood of transient flares the sky produces. EP242222 is not just one detection, it is a key that might unlock many more. There was an earlier candidate of the same kind, found before EP242222A, worth meeting because it carried a mystery of its own. It has the unlovely catalogue name 3XMM J272.4 and it was associated with a possible star cluster near a distant galaxy. Careful analysis of its X-ray flare, modelling the hot disk of debris spiralling into the black hole, yielded a mass estimate around 17,500 solar masses, firmly in the intermediate range. But it also carried a strange extra property. The black hole appeared to be spinning unusually fast. Its spin value was near 0.8, quite close to the maximum a black hole can have. That high spin is a puzzle in its own right. A black hole that grows slowly and gently, by sipping gas over long ages, tends not to spin up to such extreme values easily. A spin that high hints at a more dramatic history, perhaps rapid growth, or a major merger, or some formation path we have not fully mapped. It is one more small anomaly in a field full of them, one more object that does not quite fit the simple story, quietly insisting that we do not yet understand where these things come from. There is a particular reason a shredded star inside a dense star cluster is such a strong middleweight signature, and it comes back to that same geometry of horizons. For a very large, supermassive black hole, the region where a star gets torn apart lies inside the event horizon. The star crosses the point of no return before the tides can rip it, and it is swallowed whole, quietly, with no flare at all. For a middleweight, the opposite is true. Its event horizon is small, but its tidal forces still reach out well beyond it. So a star is shredded in full view, outside the horizon, in a burst of light we can see. And a globular cluster, or the dense core of a former dwarf galaxy, is exactly the kind of place where the only plausible central black hole would be a middleweight, not a giant. So put those two facts together. A bright tidal flare coming from the centre of a dense old star cluster is close to a signature written in the sky. A giant could not produce the visible flare from that location because it would swallow the star whole. A stellar mass black hole is far too light to shred a star into so bright a beacon. Only a middleweight fits both the brightness and the setting. That is why the candidate 3XMM J215022, tied to a possible star cluster, drew such attention, and it is why the star cluster location of a tidal flare is treated as one of the cleaner pointers toward the missing class. The place and the flare together do the work that a direct image never could. There is a sobering thought hidden in the tidal disruption method, and it is worth sitting with, because it tells you how much of this universe may be permanently beyond our reach. A middleweight black hole only reveals itself this way if a star happens to wander close enough to be shredded. But many of these objects are thought to live in quiet places, off-centre in dwarf galaxies, in old star clusters, surrounded by too little gas to ever glow steadily, with stars orbiting at safe distances. A 2024 modelling study concluded that a substantial population of intermediate mass black holes may sit outside galactic centres entirely, in exactly those quiet, starved locations. And for a black hole like that, a shredded star may be the only way it ever announces its existence, which means the ones we find are only the unlucky ones, the ones that happen to kill something recently enough for us to catch the flare. For every middleweight betrayed by a tidal disruption event, there may be many more sitting in perfect silence, in the dark, having gone millions of years without a star wandering close enough to reveal them. Undetectable, perhaps forever, by any method we currently have. The very technique that finds them depends on waiting for one of them to accidentally destroy something, and most of them, most of the time, destroy nothing at all. They simply wait. The one thing that can beat those long odds is scale. If any single middleweight only betrays itself rarely, then the way to catch them is to watch enormous stretches of sky, over and over, and wait for the rare flares to light up somewhere in the vast field of view. That is exactly what a new generation of survey machines is built to do. The Zwicky Transient Facility is a wide-field camera in California. For years it has been scanning much of the northern sky every couple of nights, catching thousands of transient flares and flagging tidal disruption events among them. China's Einstein probe, the satellite that caught E40's 222A barely 2 months after launch, sweeps the sky in X-rays with a wide field. It is built precisely to catch these events early, in the faint, slow-rising phase that marks a middleweight, and the largest leap is only just arriving. A new observatory in Chile has a mirror over 27 feet across and a camera the size of a small car. It has begun imaging the entire southern sky every few nights, night after night, for years. It is building the deepest running record of the changing sky ever made. It is expected to catch tidal disruption events by the thousands, far more than every previous survey combined. Buried in that flood will be the slow, faint signatures of middleweight disruptions, waiting to be sifted out using templates like the one EP2402222A provided. The hunt is shifting from finding one lucky flare to catching so many that the rare middleweights can no longer hide in the crowd. Patience, multiplied across the whole sky, that is the strange emotional core of this entire hunt. We are chasing a class of object that leaves almost no trace, and we can only find the rare individual that briefly, violently, gives itself away. So how do you actually weigh something you cannot see, something that gives off no light, something that only reveals itself through the behaviour of other things nearby? By now you have watched astronomers do it 3 different ways. Tonight we're going to gather those methods together, because the toolkit itself is a kind of quiet marvel. The first tool is stellar motion. Watch how fast stars or gas move near a suspected black hole, and the speed tells you how much unseen mass must be pulling on them. This is how Omega Centauri gave up its secret. Detecting a black hole this way is like standing at the edge of a crowded, silent ballroom. You're trying to prove there is an invisible dancer at the very centre, purely by noticing that a few dancers near the middle keep swinging around one fixed point far faster than any visible partner could explain. You never see the dancer, you only see the swinging, and from the swinging you deduce the pull, and from the pull you deduce the mass. The second tool is light from feeding or flaring material. When a black hole draws in gas or shreds a star, the infiling matter heats up and blazes, often in X-rays. Measure the brightness and how it changes, and you can work backward to the mass. This is how HLX1 was weighed by its impossible brightness, and how the tidal disruption events were weighed by the shape of their flares. The black hole stays dark, the wreckage around it does the shining. The third tool is the newest, and in some ways the purest: gravitational waves. When two black holes merge, they send out those ripples in space-time, and the exact pattern of the ripple encodes the masses of the objects that made it. This is how JWST 521 delivered that firm 142 solar mass measurement. No light at all, just the shape of the tremor. It is the only method that weighs a black hole directly, from the pure gravity of its birth, with nothing in between. Notice what every single one of these methods has in common. Not one of them shows you the black hole. Every piece of evidence for this entire missing class comes from watching something else behave strangely nearby. A star swinging too fast, a flare too bright, a ripple lasting under a second. The black holes themselves have never once been seen. They are inferred always from the wreckage and the motion they leave in their wake. That is the deep and permanent oddity of this subject. We are certain black holes exist, and we have never looked at one. We only ever look at what they do to their neighbours. The toolkit tells you how to weigh a middleweight. It does not tell you how one is born. Tonight we're going to look at how one is made, because the question of formation is where the field is most alive right now. There are three competing ideas for how the universe makes an intermediate mass black hole, and they may all be true at once in different places. The first pathway is the runaway collision. Picture a young star cluster, freshly formed, extremely dense, packed with stars crowded far closer together than anything in our neighbourhood. In such a crowd, stars do not just orbit peacefully, they collide. And when two stars merge, they make a bigger star, which is a bigger target, more likely to collide again. So a runaway begins, collision feeds collision. One growing star at the crowded centre swallows companion after companion in a chain reaction. It has been compared to a slow-motion demolition derby playing out over thousands of years. This central survivor swells past 1,000 times the mass of our Sun, an unstable giant that cannot possibly last. And when it finally collapses, it leaves behind a middleweight black hole seed. This is not just hand-waving. It has been modelled in detail on supercomputers. Recent simulations, including a Japanese project led by a researcher at the University of Tokyo, and further work in 2025 using direct star-by-star calculations, have shown that this runaway process can build a very massive star. In some models, it exceeds 50,000 solar masses, and from it comes an intermediate mass black hole. It can happen quickly, in the very first dense star clusters of the early universe. The demolition derby works, at least in the simulations. It is worth watching the runaway collision unfold slowly, because it is one of the most vivid processes in astrophysics. Begin with a young star cluster, freshly born, so dense that its central stars are packed thousands of times closer than the stars near our Sun. In such a crowd, near misses become collisions. Two stars graze, merge, and become one heavier star. Now that merged star is bigger. A bigger star is a bigger target, and a heavier star sinks faster toward the crowded centre, where the collisions are thickest, so it collides again and again. Each merger makes it larger, which makes it collide more, which makes it larger still. This is the runaway. A single star at the heart of the cluster grows by devouring its neighbours in a chain reaction. It swells past 100 solar masses, past 1,000, in some simulations climbing toward tens of thousands of solar masses. It becomes a bloated, unstable supergiant, a star with no stable future, far too massive to live long. And when it finally exhausts itself and collapses, it does not leave a small stellar mass remnant. It leaves a middleweight black hole seed, born whole from the wreckage of 1,000 smaller stars. Recent star-by-star simulations tracking each star individually through the crowd have shown this can happen fast, within the first few million years of a dense cluster's life, especially in the earliest, densest clusters of the young universe. It is a way to build a middleweight without any pristine gas cloud and without any prior black holes. Just an ordinary crowd of stars packed tightly enough that they cannibalize their way up to a black hole. The second pathway is the direct collapse we met earlier, the one that may explain the heavier seeds and the overmassive early monsters. A giant, pristine gas cloud in the metal-poor early universe, unable to cool and fragment into stars, collapses straight into a black hole of 10,000 to 100,000 solar masses. It never passes through a stellar life at all. This is the pathway that makes the biggest seeds, and it is the one UHZ1 seems to point toward. The third pathway is the hierarchical merging we met with G190521. Black holes merging with black holes in dense clusters and galactic nuclei, each generation heavier than the last. They stack upward through the forbidden gap and into the intermediate range through sheer repetition. This is the pathway that leaves fingerprints in gravitational waves. The 85 and 66 solar mass progenitors of JWST 19521 are its best evidence. The hierarchical merger pathway deserves a closer look, because JWST 90521 turned it from speculation into something we have arguably watched happen. Picture a dense environment thick with black holes, the core of a globular cluster, say, where hundreds of stellar mass black holes have sunk to the centre and crowd together. In that crush, black holes find each other, pair off, spiral in, and merge. Each merger produces one heavier black hole. Now the key question is whether that new, heavier black hole stays in the cluster or gets kicked out. Every merger gives the final black hole a recoil, a shove from the uneven blast of gravitational waves. If the shove is hard enough, the black hole is ejected into space and its climb ends there. But if the cluster is dense enough, its gravity can hold on to the merger product despite the kick. And if it holds on, that heavier black hole can find another partner and merge again. Generation upon generation, each one heavier than the last. The black hole marries upward through the forbidden gap, one merger at a time, until it reaches the intermediate range. This is why the 85 and 66 solar mass progenitors of GW190521 mattered so much. Sitting inside the forbidden gap, they look like second-generation black holes, themselves the products of earlier mergers, caught in the act of climbing one rung higher. It is a slow, patient staircase built entirely in darkness and silence. Each step a collision, each collision a ripple in space-time. The black holes assemble a middleweight by stacking their own kind, over and over, in the crowded dark. Runaway collision, direct collapse, hierarchical merging. Which one actually makes the middleweights of the real universe? The honest answer in 2026 is that nobody knows for certain, and there is no consensus. It may be that all three occur in different environments in different eras, each contributing its own share to the missing population. A very massive, dense cluster might build one by collision. A pristine cloud in the early universe might build a heavier one by collapse. A crowded galactic nucleus might build one by stacking mergers. Three roads to the same hidden destination, and we are still working out which roads the universe actually travels most. There is a thread here that ties the newest observations to the oldest theory in a satisfying way. The idea of the middleweights goes all the way back to those papers of the early 1970s, pure prediction, decades ahead of any means to test it. And the first real observational category proposed to house them came in the 1980s, with the discovery of those ultraluminous X-ray sources, objects too bright to be ordinary stellar mass black holes, the class that HLX-1 belongs to. So the hunt has been running for half a century, from a theoretical guess to a category of suspicious X-ray sources, to gravitational waves, to tidal disruptions, to the sharp infrared eyes of James Webb. And a 2026 study drew one of the most satisfying connections of all. It took the distant, dense star clusters that James Webb has newly resolved in the early universe. It ran the internal dynamics forward, and it found that clusters of 100,000 to 1,000,000 solar masses could form black holes of a few times 10,000 solar masses through their own internal processes. The star clusters James Webb sees forming in the deep past are plausibly the very nurseries where today's middleweights were born. The threads are converging. That is the feeling in the field right now. Not a single triumphant confirmation. Instead, many separate lines of evidence, from many different methods, all leaning the same direction. All pointing at a population of objects that theory says must exist. Objects that keep almost being caught, and that have not yet quite been pinned down beyond dispute. Let that be the honest shape of it. The missing class is not missing because the universe lacks them. It is missing because they are the hardest large objects in nature to see. Too heavy to be born from a single star. Too light and too quiet to sit blazing at a galaxy's core. Living often off-centre and starved in the outskirts of small galaxies and old clusters. Giving off no light. Betraying themselves only when a star swings too close, or when two of them collide, or when a whole swarm of stars whirls around an invisible centre faster than anything visible could explain. We have found the closest one hiding inside a naked-eye cluster 17,700 light-years away, holding 7 runaway stars on invisible leashes. We have found the brightest one blazing in the outskirts of a galaxy 290 million light-years away, 100 times too bright to be small. We have heard the firmest one born in a tremor that changed the length of a laser beam by less than the width of a proton. We have watched one betray itself by slowly tearing a star into glowing threads over the course of years. And we have found early monsters so overmassive that they seem to demand exactly these seeds to explain how they grew so fast. Every one of them a candidate, every one of them a piece of the same missing rung on the cosmic staircase. And somewhere out there, in the quiet dark between the stars, in the starved outskirts of countless small galaxies, there are almost certainly many more, sitting in perfect silence, waiting for a star to wander close enough to reveal them, or waiting forever. You do not need to hold any of these numbers in your mind now. You do not need to follow the physics or remember which black hole weighs which. Let the whole picture soften and drift. There is nowhere you need to be, and nothing you need to solve tonight. The hunt has been running for 50 years, and it will still be running in the morning. The 7 fast stars will still be whirling around their invisible centre. The flare from a shredded star will still be fading slowly across the dark. You can let all of it move quietly along without you, the way the cluster moves, the way the ripple moved on and on through the calm and silent vacuum. Think, if you like, of that hypothetical planet inside Omega Centauri. The sky never fully darkens. Thousands of stars brighter than Venus hang edge to edge in a perpetual soft twilight made entirely of suns. Somewhere near the centre of that blazing sky sits the dark thing we have been chasing all night, invisible, patient, holding its 7 runaway stars in place, keeping it secret as it has for billions of years. It is not lonely. It is not restless. It simply is. A knot of gravity so complete that light forever falls in and never climbs back out, waiting in the middle of 10 million suns. And far beyond it, in the outer suburbs of a galaxy nearly 300 million light-years off, the bright X-ray beacon of HLX-1 goes on pouring out its impossible light. The exposed heart of a galaxy that was swallowed long ago, and farther still, at the edge of what we can see, the overmassive black holes of the infant universe still burn in the images James Webb has gathered. Monsters that grew backwards, that got too big too fast, quietly insisting that somewhere in their family tree there must be a seed, a middleweight, a bridge across the gap. The gap will be filled in time, perhaps by a future gravitational-wave detector, a great instrument in space that could hear middleweight mergers ringing out across the cosmos. Perhaps by deeper surveys catching more slow-rising tidal flares, each one a black hole betrayed by an unlucky star. Perhaps by James Webb, or the telescopes that come after it, finally catching that faint accretion glow in Omega Centauri. The glow that has so far been just too dim to see. The tools are getting sharper, the threads are converging, the chair set at the table for the missing guest may not stay empty forever, but tonight, the middle of the staircase remains the most beautiful open question in the study of black holes. A whole class of objects that must exist, that theory demands. It keeps almost stepping into the light and then dissolving back into the dark, certain enough to name, elusive enough to have hidden for 50 years, close enough to touch in a cluster you could see with your own eyes on a clear southern night, and still, after everything, not quite caught. You have travelled a long way tonight, from a black hole no wider than a city, born from a dying star, out across an empty middle nobody could fill, up to the silent monsters at the hearts of galaxies. You have met the 7 whirling stars and the impossible X-ray beacon, and the tremor in space-time and the star pulled slowly into glowing threads. You have stood at the edge of the ballroom and felt the invisible dancer at its centre, and you now know why a missing size of black hole has quietly become one of the great unfinished searches in all of science. No one expects the answer to arrive all at once. It will come the way it always comes in this field, one faint signal at a time, one candidate at a time, one flare and one ripple and one whirling star at a time, until the weight of evidence grows too great to argue with, the way it did, in the end, for Cygnus X1, when even Stephen Hawking had to concede. So rest, now. The stars in Omega Centauri will keep their long, slow orbits without any help from you. The dark thing at their centre will keep its patient watch, and the great telescopes will keep listening all through the night for the faint voice of the missing black holes. Wherever you are and whatever brought you here, you can set all of it down for a while. Sleep well tonight. And from all of us drifting out here in the deep and quiet dark, watching the middle of the staircase, waiting for the missing rung to finally step into the light, good night.